So I would like to introduce our next speaker of this Princeton series. Her name is Zhurun, Judy G. For some brief background, Judy G is a philosophy fellow at SLAC's National Lab and will become a faculty member at MIT's physics department at the end of 2025. Regarding Judy's research, she's interested in developing novel scanning probe experiments to study quantum phenomena, like electron correlation and topology in two-dimensional materials. Today, we will learn more about these studies, as Judy will explain at the talk, titled An Introduction to Microwave Sensing of Quantum Materials. So please join me in welcoming Judy to the stage.
Can everybody hear me in the back? Great. So thanks to the organizers for giving me this opportunity to give a lecture, but I felt like I'm not enough for that. So it's more like a discussion on the broad topic of microwave sensing of quantum materials. And before I start, I would also like to do a small poll, like how many of you have been working with microwave before? Either theory.
Yeah,
microwave oven, okay. Except for that. Yeah, so seems like all of you have worked with microwave before. That's great. There's like an incomplete timeline of how microwave has been used in the condensed matter field, starting from the theoretical foundations of Judy model, Hubble formula, as well as the Debye model for insulators. That's 1900. Then starting from 1940, this was also the time after World War II that the radar and every microwave technique came into play. People started measuring bulk cavity and surface impedance, as well as noise, Johnson noise spectroscopies. I think maybe the first paper on Johnson noise in condensed matter was by Dickey, the Dickey fellow Dickey here at Princeton, and also magnetoresistance, magnetic resonances. So after that, in 1960s, there was the development of a vector network analyzer, and in 1980s, the gallium arsenide HEMT, so that's amplifier and other type of cryogenic low noise amplifiers. So this made it possible to do many cryogenic experiments without heating up the sample too much. Then starting from 1990s, there are two more threads. One is like on-chip development. So now you can send in microwave onto a microchip, and you can do lithography type of work to measure smaller samples, and also on tip. So there's a scanning mode of microwave impedance microscopy where it allows you to do more precise spatial resolved measurements. And now more and more efforts have been put into quantum limited measurements, where we call it quantum sensing of quantum materials. And here I call it incomplete because there are other many threads that is not like included here, including the terahertz spectroscopy. It has kind of some overlap with the microwave sensing as well after do the Fourier transform. But it kind of gives you the idea that microwave has been used since a long time ago for this field. So here's my outline. I will start with some fundamentals and context, and then provide two brief examples, one for superconductor sensing and one for fractional state sensing. And then I will end with some new techniques and open questions. So first of all, why microwaves? Well, microwave, it's in between the frequency of well-known DC measurements or electronic measurements and the high frequency optical spectroscopies. And in the middle, there are all types of different excitations happening. The magnons, the superfluid excitations, and plasmons and polaritons. It's also in the frequency regime where you can access different omega tau type of limits Or to say, in a very broad definition of the microwave regime, emits from 300 megahertz to 300 gigahertz, or sometimes people also call this millimeter wave. In what sense? Whatever. The energy scale is micro EV to milli EV. So it mostly senses low energy excitations, or in many cases, also ground states of materials. Well, it's relevant to a lot of materials, but I would like to start with a brief recap of the electrodynamical building blocks. These are just like Maxwell's equations and some of the constitutive relationships here. So the measured quantities would be materials related, and in many cases, the microwave field can be precisely described by the electric field, oscillating electric field, and magnetic field, and you can solve the Maxwell's equation to get all the electrodynamics there. But also, just to simplify it and also to sort of like make a connection with microwave engineering, many people also use the concepts like impedance and admittance and use a lumped element model, namely simulate the circuit as L, C, and R, those like electric components or circuit components. And here, the impedance and the admittance just describes a material's response to a microwave. And here's the complex permittivity and the complex conductivity that relates the current generated in the Maxwell's equation from the electric field. For example, the complex conductivity here has the real and imaginary part. These two are kind of interchangeable. I try to make it unified in my talk, but sometimes you may see both of them. So the kind of idea is like comparing to the DC measurements, you do not only measure this conduction part, but you also measure this bond charge contribution, or it's displacement, where you call it polarization or whatever. So these two parts would kind of form the most important physics quantities for every single thing you will see in the rest of this talk. And then we can do a simple case analysis for metals. Simplest metals in the classical free electron picture, but it turns out to be working pretty well for many of the materials that we measure because the frequency is low enough. Here's the equation of motion describing that the kick of the electron or the acceleration is kind of provided by this microwave field, but it also has this like collision or just a relaxation time term. And then the AC conductivity can be directly written out as having this real and imaginary part. The real part describes the dissipation, and the imaginary part describes the reaction or the inductance. So there are two regimes. When you are at a very small frequency, then your material is mostly resistive. The extreme is like DC measurement. You just measure resistance. But then when you go to a very high frequency, then the material becomes more and more reactive, and then the energy stores in inertia. So another way to understand this is like when you shake this water tank, when your frequency is very low, it just follows your wave. So everything is in phase. But then when you shake it like more vibrantly, then what happens is that it has a lag. So that's like the inductance. So the current has a lag compared to the electric field that applies to it. And then there's a bit of contrast between the 2D case and the 3D case. In the 3D case, we solve this continuity equation for the Maxwell's equation. And then you will find there's a skin depth, namely microwave can only penetrate through metal for a certain distance. For 2D, on the other hand, because it's too thin, you cannot really like screen the microwave completely. So then you can directly calculate it by a surface boundary condition, like a surface current type of thing. And then talking about the circuit model, that's to simplify the whole physics picture and for the calculations ease. Here, the resistance 1 over sigma has the real and imaginary part. and it can be seen as a resistor and an inductor in series. So then the resistor is about the real part of this conductivity, and the inductor is the imaginary part of the conductivity. That's how the electric field and the current is related to each other. In contrast, for insulators, it's the other extreme. You can use the Debye model to talk about the polar dielectric response. Here, the imaginary part of the permittivity is the dielectric loss, or the dissipative part. When it's ideal, you probably don't have too much dielectric loss. And then the real part of permittivity, on the other hand, is the energy stored in polarization. So the AC electric field really drives the polarization, and that has energy stored into it. So here, again, there are different frequency regimes. When the frequency is really low, the dipoles track the field really well. So namely, most of your response is kind of like in phase, and you have very large, the real part of this dielectric constant where the permittivity and small loss. And when you have omega tau approximately equal to 1, where they're comparable to each other, this is when the loss tangent peaks, because the phase shift is around 45 degrees and you have the most energy lost. But when you go to the high frequency regime, then the dipoles just cannot track the field anymore. So then there's nothing they can do. You're mostly reactive. There's not too much loss. And again, the circuit model here would be a resistor in parallel with a capacitor. The capacitor has to do with the real part of permittivity. The resistor has to do with the imaginary part of permittivity. So the reason that I talk about all this is because the materials microwave responses are kind of just the quantities that we measure again and again and again. That's kind of the essence of microwave measurements. We've talked about how metals behave, and then the surface impedance is related to its conductivity. And the dominant physics here, you have this impedance going in the like square root of omega type of fashion when omega is small. Omega is a frequency here. When you have a dielectric, on the other hand, you have this loss peak. Then the third case is a superconductor. A superconductor has a loss channel. Loss channel could be coming from the type 2 vertices, or it can be coming from just like pair breaking, or your temperature is too high, it's larger than Tc or something. And then it has this imaginary part. This imaginary part is inductance. It's the kinetic inductance of the quarter pairs. And then, as you can see, it has to do with the D. D is the thickness of the superconducting film. So that's to say, when the D becomes very thin, so D is very small, then this term becomes very large. So in 2D superconductors, the kinetic inductance term really dominates. It has a lot of weight. And the physics were featured here. You have really low real part of the impedance, or just your loss is really small, until you have some pair breaking, where you have vertices, you have those quasi-particle excitations. And for magnetic materials, on the other hand, essentially you have this like mu inside. This permeability can be also a function of frequency. And more importantly, the ferromagnetic resonances, the spin resonances, and so on, often happen also in this microwave regime. Okay, so having talked about different responses from different materials, then the next question is, how do we measure them? There's no ideal microwave voltmeter or ammeter like in the DC case, because, for example, a voltmeter needs the impedance to be really large. It needs the inner resistivity, for example, for it to be large enough such that it can accurately read out the voltage. But there's no such thing in the microwave regime. So instead of using a voltmeter or ammeter, you use a VNA, or in some sort of way, you use 2 ports to hook your device under test, this DUT's device, or your material with 2 cables. And then you use a device to measure it. And those cables have a characteristic impedance of 50 ohm. So everything, instead of seeing the voltage and the amp directly, you control the waves in a 50 ohm fashion, and then you measure how much energy comes in, how much energy goes out. So it's a bit like optics analogy, where a wave impedance impedes on the interface, and a part of it will be reflected, a part of it will transmit through. So then here, you're also measuring like how much got transmitted through, how much gets reflected. And then, so there's a quality factor Q for some of the devices, namely, if just hooking up your device with a measurement instrument is not enough, then you probably want your microwave fields to be larger. And one way to make it larger is to embed your device or material inside a cavity, or sometimes people call it resonators. And the way that enhances the microwave field is by having a lot of oscillations of the microwave field inside it at specific frequencies. And this quality factor just determines or describes how many optical cycles energy circulates before dissipating out of it. And then here, when you have a quality factor Q in your cavity like this, then your electric field enhancement goes with square root of this Q. And with this type of enhancement, usually you can get a lot more signal to noise ratio in real measurements. But it also comes with, somehow it doesn't show. Okay, okay. So you also compensate something to get this higher sensitivity, which is you would only get the energy enhancement at specific frequencies. So it's hard to measure this thing with a broad spectrum. And then here's how the measurement goes. So you can imagine having a port 1 and a port 2, and both of them having a characteristic impedance of 50 ohms. And in the middle, that's your device with some other impedance to be measured. And here, by the way, the 50 ohm is kind of a standard that was made by the military, I think, because like 30 ohm and 70 ohm are kind of the characteristic impedances that can maximize the RF power transmission. So they kind of just adopted that value. So all the coaxial cables that you can see are mostly at 50 ohms now. And then from port 1, you can have some incident wave. And then from port 2, you have transmitted wave. But also the part of it will be reflected from port 1. So we call the amplitude here A1, and the transmitted as B2, reflected as B1. And then you can also hook up in the other way so that you transmit microwave from port 2 instead, and then you measure how much gets transmitted out from port 1. Because there are 4 different ways that you can excite and measure, it is a matrix of S parameters. And each of them describes this ratio between the in and out. So S11 and S22 are the reflection, the S21 and S12 are transmissions. As an example, S11 is a ratio between B1 and A1. So that's the reflectance. And here the reflectance can be directly written when you solve the wave equation as the ratio between Z load minus Z none and Z load plus Z none. So if your Z load is not 50 ohm, it's not like every else component in your circuit, then S11 will be non-zero. That's to say, whenever your impedance does not match, you will have a back reflection. Sometimes the back reflection is needed if this is your sample, but sometimes the back reflection is not unwanted. The reason is you don't want too much power to be dissipated along the line or to be directly reflected before it even gets to your measured sample. So then in many cases, that becomes a problem. And so when measuring how much the device is actually changing your signal, we want to introduce something called the impedance matching. So this is a concept from microwave engineering. Namely, we have a source and it has a characteristic impedance of 50 ohm. And we want to maximize microwave power delivered to the sample by making the impedance that it sits behind it to be the same as its own impedance. But you can see here, when Z load is not xenon, a part of the wave just gets reflected back. So instead, we add a matching network to it. And this matching network could transform the impedance to make them close enough to each other. And a simple way of doing that is through a quarter wave transformer. As to say, behind or in front of your device, you first hook up a lambda/4, lambda being the wavelength of interest, length of cable. And that cable can convert the impedance to close enough to the input impedance. And then you also can use stub tuners by putting specific amounts of resistance. And also there are other strategies of broadband matching circuits. So all those are kind of like just helping you getting more signal to here and also measuring more signal when it comes out. Yeah, and here's the trade-off. No matter what you do here, the broadband spectroscopy was going to be very hard. This is a difference between optical spectroscopy. You can easily tune the frequency here. If you want to optimize the signal, you can kind of sacrifice this aspect. Okay, so before I move on, is there any question about the fundamentals? Okay. Oh, one question.
Earlier you showed the for metal, for example, impedance one square root omega.
Yeah.
Is there a simple way to understand that?
Oh, you can one can directly get that from here. So yeah, it's just because the impedance relationship with the conductivity. And then when you plug in the Zhurun model, you can directly see that.
It's because the skin depth.
No.
The square root omega.
Oh, you mean where the square root comes from?
Yeah.
Okay. So here, oh, sorry, here. So because like the Z, the impedance has the form of this. So the square root omega is already in here. Yeah. So yeah. So the idea is that when you're at very low frequencies and your resistivity here or the conductivity is not changing too much as a function of frequency, then this square root of omega just comes in.
Just the derivation from
Yeah, it's a derivation. But it also, yeah, as you said, it has to do with the skin depth, because that this is indeed derived by the continuity. Yes. Okay. So then, if no more questions, we can go to this section of how people use microwave to study superconducting states. Here. Okay. All right. So first is a why we use microwave spectroscopies to study superconductors instead of using DC, for example, or using high frequency optical spectroscopies. Well, one reason is the frequency really matches. The frequency matches many of the quasi-particle excitations in superconductors and the gaps, as well as the collective modes. So then directly, if you get a microwave spectroscopy, then you can already tell a lot of those things. And another thing is because the microwave can interact with both the conduction electron, as in the way that DC field does, and also Cooper pairs. So because it's oscillating and it probes the kinetic inductance, so then its real part of the impedance has to do with dissipation, and it probes those quasi-particles. So the imaginary part probes the inductive and the superfluid responses. So one way of thinking about how the superfluid responses contribute to the microwave response here is to see, imagining you are pushing like a snow skate type of thing, but there's not too much friction, so that's not dissipation, but still you have some inertia, and that inertia is exactly the inertia that the Cooper pairs feel, and because of that, it has a lag, and that lag has an energy stored in this inductive part. So 1/2 Li squared, so that's kind of the energy that this circuit has in the inductor, is exactly the energy or the kinetic energy of all those Cooper pairs. So then you can calculate the inductance from that equation, and you can directly get that the inductance is 1/, the density of Cooper pairs, or superfluid density. And then the impedance is just Y omega times this inductance. So that's how the microwave, the intrinsic property of the superconductor is related to a quantity that microwave spectroscopy can measure. This is one of the very first early experiments that Glover and Tinkham at UC Berkeley in 1957. So what they did was they used different microwave sources at specific frequencies. So they span like a really large frequency regime, and they measured the real part of the reduced conductivity. It's actually like a thin film measurement, and they send in microwave, measure transmission, and from that transmission back out the conductivity. And then as shown here, it starts with a pretty small number, and gradually it increases and saturates. And the point where it gradually reaches saturation is when this frequency reaches the superconducting gap. So that's to say, when your frequency is below the gap, you don't have too much quasi-particle excitations, but once you're outside of the superconducting gap, you have a lot. So that's kind of the idea. And also they measured as a function of temperature. And here, this is all below the transition temperature from 0 to 1 T/Tc. And this is the imaginary part of the conductivity. So the left graph is about the dissipation. The right graph is about the kinetic inductance. And here, the sigma has this type of exponential increase as the temperature drops, and gradually it saturates again. So here, this exponential increase of sigma is directly related to the S-wave pairing. So for this type of gap, so BCS theory can directly give you this type of behavior of density, superfluid density, and then if you calculate sigma 2, that will have this behavior. So this was the very first experiment that kind of proves the BCS theory and all the things about the superconducting gap. But later on, there have been more and more efforts to make this experiment more versatile. For example, if you want larger signal to noise ratio, if your sample is not like a super large film, because they started with measuring just like tin and lead films, so you can easily get a large area and large signals. But here, they measured like a smaller 3D crystal. So this is a measurement on the, it's a F electron, yeah, I think it's a F electron cuprate-like high temperature superconductor. But then in this type of measurement, we really want the signal to be larger, so embedded the crystal inside a 3D microwave cavity. So this is a 3D cavity made of copper. And then this cavity has resonances at different frequencies. So this is a fundamental frequency, but then you can also have its higher harmonics. And all this harmonics would give you enhancement of electric field. So as you can see, they hooked up the VNA to send microwave in and to measure the microwave coming out. So that's a type of reflectance measurement. And here they plotted as a function of temperature in the left-hand side figure, and then the right axis is sigma 2. So sigma 2 here is about the superfluid density again. And as a function of temperature, it shows a pretty linear increase when the temperature drops. So it's different from the tin and the lead film the previous study was talking about. Here, instead of like an exponential type of increase, it's a linear type of increase. And this linear type of increase is directly related to the heat wave type of nodal structure. So, so then they use the microwave study here to prove that this material has a D wave pairing instead of an S wave pairing. But you can also see here that they measured at different frequencies from 0.13 to 19 gigahertz or so. So all those different frequency measurements can also tell you something about the quasi-particle and the scattering dynamics. So here, the linearity has to do with the nodal semiconductor. But then, because the nodes can also lead to frequency-dependent dissipations, even from very small frequencies, unlike in the case of S-wave superconductors. So then, through measuring the sigma 1, they got information of these quasi-particles, and also the frequency dependence always has this quasi-particle lifetime in it, just like in the Zhurun model for a common metal. Here it's similar, so then you can get hands on what the lifetime is. Okay, and this is a more recent microwave sensing measurement, which is the kinetic inductance sensing using 2D superconducting resonators. And here, this is MATBG, because yesterday Alan has talked a lot about MATBG, so I won't go into detail, but the idea is that it goes at a magic angle, it superconducts, and people are still thinking about what type of pairing symmetry it has, and what's the TC and what is really happening there. So this is from William Oliver and Tapple's group, 2025, but also see other papers this from Philip Kim's group in a slightly different strategy. So you have a lambda/4 resonator, and this is a on-chip aluminum-based resonator that has a very high quality factor. A high quality factor just means that your sensitivity is high, or to say your electric field is really enhanced at its resonance. Its resonance is characterized by 1/2 pi square root of L1C. So L is the effective inductance of this resonator, and C is the effective capacitance. But then what they did was they put on this material to be a part of this resonator. So they kind of connected the resonator by this material. It's a type of inductive coupling. And then because of that, the total inductance is changed. So now the total inductance has not only the part coming from the aluminum resonators, but also the part coming from the MATBG. And they can also sort of tune the gate voltage of the MATBG to get to different states and see how this like effective inductance changes. And here, by measuring the resonance shift, we know the inductance. From knowing the inductance, because it's proportional to 1/, the superfluid density, then one can directly get the information about the superfluid density. So that's kind of the idea, but with like higher resolution, and then definitely, if this is the type of scheme that's needed when your sample is only on the micron size and with nanometer thickness. And here are some signatures of the superconducting domes that they saw. So here, for example, when tuning the backgate voltages, so you're tuning the filling. And in this dome and that dome, so these are the two superconducting domes that can be verified by DC transport. They could see the frequency having a large shift. But when the backgate voltage is elsewhere, it doesn't have this much shift. So that means that this shift is characterizing the superconducting phases. And here's a more zoomed in like measurement. And then they saw this dependence of the DS. DS is superfluid density as a function of the carrier density. So now the microwave measurements would allow you to tune the gate voltages, to tune the material properties while you measure how much superfluid density you have there. And indeed, it is very large when you go into the superconducting dome. So that's the kind of the idea. So these are three representative measurements on superconductors that hopefully have given you an idea that microwave is a good frequency regime for measuring those superconductors. And then I will switch the gear a little bit to a different scheme with spatial resolution for imaging fractional edge space. First, I will start with the technique, the microwave impedance microscopy. So as we know, the microwave wavelength is on the centimeter scale. So it's like super large, but in many cases, the length scale of interest in the quantum materials is only on the 10 to 100 nanometer scale. So we cannot see the line here because like there's so large contrast. So then we really need a way to somehow confine the microwave such that it can give us information of a very small domain size. So one way of doing that is through confinement on a metallic tip. So the tip acts like a small antenna. It's long, but it's like narrow or like small in diameter. So its diameter can be on the scale of 50 nanometers or 20 nanometers. And then you send in gigahertz wave instead of directly from leads on the sample, you're sending through the tip. And when you're sending microwave through the tip and sample has a coupling. And that coupling can be written in this circuit model here. You have a capacitance at the interface of tip and sample, and then the sample has a resistance, a resistor and a capacitor. So it can be modeled this way. So then we measure the reflected microwave coming out of the tip. It's slightly different from the far field or global microwave measurement, such that here the sample is only inducing a perturbation of the signal. It's not the full signal that you measure from the reflectance. So that's to say, if we define the reflectivity as gamma, so gamma is around gamma none, which is the case when you don't have the sample underneath, and then you put on this small perturbation, d gamma over dy, and ys is the sample admittance. So then with that small perturbation, we can directly get this information out there. But also because it's only a perturbation, the real and imaginary parts now do not have a one-to-one correspondence with sigma and prime and sigma double prime, or to say it doesn't have one-to-one correspondence with the dissipation part and the inductive part. Instead, here we can do some finite element simulations to get a different dependence. So the y-axis is the sample resistance, and the omega being the frequency, and also the permittivity. So it goes from one extreme to the other, and then the y-axis has the two channels of the microwave coming out. So one channel is the reflected wave, but in phase with the coming in wave. and the other part is out of phase. So as you can tell, if we focus on how it depends on the sample conductivity, then the more insulating you'll get, if you look at the right-hand side, the more insulating you'll get, the smaller of this imaginary part you get. And then it monotonically increase when you go to the other side. And similarly for the real part, you also have a lot of sensitivity when you're at the intermediate conductivity regime. But then when you go to very insulating, like a perfect insulator or a perfect metal, it becomes very small. So that's how we get some sensitivity to the local conductivity. And that is a way of doing those DC measurements. So here there's a little bit of more zoom in, but just from the technical part of how this thing actually works. So we have microwave source coming in, and it has an excitation line. The excitation line goes through a directional coupler and then an impedance matching circuit and goes onto the tip. And the reflection comes out back from the impedance matching circuit, goes through the directional coupler, but it's designed such that it can go only to the right. And then goes through tip bias, the code amplifier at 4 Kelvin to amplify the signal, and it goes to this IQ mixer. So this mixer just down converts the microwave field to DC, because at DC, we can have different lock-in type of measurements where we can get both the DC part of MAM and also the AC part. If we modulate the signal, we modulate the tip by its height, we modulate the bias applied to the tip or gauge on the sample, etc. Then we can also get the dMIM over dZ or d this quantity. So then there's also a cancellation circuit that is just for not kind of having too much back reflective signal, not coming from the sample, but from elsewhere of the circuit, because having too much of that, it may just sort of like make the gain of the amplifier jeopardized, because it will get to its maximum too quickly. So yeah, so because of that, we now have this whole circuit of sending in wave onto the tip and then measuring the reflection coming out of the tip with some amplification or gain, and go out with some measurement circuits. Okay, so with this type of technique, it has been proven to be an excellent probe of local electrical properties. So many of those properties only happen in the tens of nanometers scale, but then we could see the quantum Hall edge states, the quantum spin Hall edge states, and the quantum anomalous Hall edge states. So those are many of the examples of measuring 2D examples. There were also other examples of measuring those magnetic domains, were polarized dielectric domains, ferroelectric domains, and such. Okay, and I would like to give a little bit of focus on the fractional states. I think both Moti and Bien and others have talked a lot about this. I won't try to go into the theoretical details, but just from the perspective of what microwave can see in such type of a system. So in the book, if the energy gap of those fractional states are reasonable, then in the microwave regime, you will see a gap in the book. Now on the edge, because of the interaction, you will see the 1D Lottinger liquid type of model driven where described chiral edge modes with some interaction parameters G. Well, you might know the result that if you have a quantum point contact and a tunneling barrier, then through that tunneling barrier, when you measure the tunneling current, this current has some like power law relationship with this interaction parameter. But in the AC field, there's actually another dependence, which was also proposed by Wen in 1990s or so. And then, so the AC conductivity has a frequency dependence that goes through omega 2g minus 2. So this is another type of power law relationship that may be helpful for understanding this type of fractional states. But more than that, what happens on the edge is you have some electric fields and magnetic fields now perpendicular to each other, and classically that would just induce charge drift. And this type of charge drift, when you have Coulomb interaction or long-range interaction, it forms edge magnetoplasmons. So, and when you form edge magnetoplasmons, it can have oscillations and peaks in the microwave region. So this is another thing that microwave can presumably see. And then the last thing is when you have some sort of like the hole-like states instead of the electron-like states because of the hierarchy relationship or the particle-hole symmetry, then instead of having one edge state, you might have edge reconstruction. You might have multiple edge states and so on. So all those things were of interest when we got into this field to see, to try to use our tip to see what happens here. And so we recently measured this twisted molybdenum, which is a fractional term insulator that was first demonstrated by our collaborator at UW Zhurun's group. And it all began with the McDonald's model, Allen's model, on this valence band, topmost valence bands of twisted molybdenum because of the band was flat enough, the kinetic energy was suppressed enough, and also because there's non-trivial topology of the bands due to this fermion type of texture. So at partial filling, there was conjecture that there could be fractional translating states as the band analog of those fractional quantum Hall states. And indeed, our collaborators saw this type of quantization in transport at nu equals to minus 2/3 in this material. As you can see here, this is vanishing Rxx, and the Rxy forms this quantization there. So then they measured that result using transport. And as you can see, for Rxx, it has a vanishing component. So it's close to 0 when it's close to nu equals minus 1. And it's also the case when it's close to nu equals minus 2/3. So that was the signature. So we also tried to use MIM to look at this particular system. And the result looks like this. So here the maximum means more conductive and the minimum means more insulating. And then as you can see, near nu equals to minus 1, and when the displacement field is small, the y-axis is displacement field, the x-axis is the carrier density or the doping. Then here, there's an insulating regime. And similarly, at nu equals to minus 2/3 and nu equals to minus 3/5, there were 2 blobs of insulating regimes. So that shows good correspondence with the Rxx that they measured in the book. So effectively, you can see that this microwave probe, when the tip is sitting inside the book, acts as a local conductivity measurement. And what's more, so our microwave probe is actually very sensitive to pretty insulating materials. For example, in transport measurement, DC transport measurement, when the filling factor is very low, where it's very close to the charge neutrality, because twisted molybdenum is a semiconductor, so then the contact resistance becomes super large. And when the contact resistance is large, you will see something like this black region, which cannot be very well resolved. But in the case of microwave measurement, you don't have that concern. You are capacitively coupled to the material. So because of that, we could zoom into this like low fractional filling case, and we saw minus 1/3, 1/4, and minus 1/6 features. And especially we tried to turn on a magnetic field to see the -1/3 whether it has any shift, and we didn't see any shift. So that was how we got to the conclusion that for this specific twist angle or sample, the -1/3 is not a fractional state, but instead is topologically trivial. Yes.
Maps are from the average over the spatially, or is it just from something particular spatial?
This is from a particular spatial point, but when you go around, it's pretty much all look like this, with within some fluctuation of twist angle disorder and other disorders. Yeah, and so that is a change from a contact resistance dominating case in this like small filling factor region to a contactless type of measurement.
So question. So
yeah,
in your MIM measurement, you only get is that the case? You only get relative conductance mapping in the base map. So if I was measuring this data on the first time and without the transport measurement in reference, how can I tell? Okay, this is 2/3, this is 5/3. Yeah, this is 3/5, 5/5, or like different states. Right?
Okay, yeah, that's a great question. So I'll start with how do we know which one is 2/3, which one is 3/5?
Yeah.
So we can do very similar thing as DC transport. We turn on magnetic field. We calculate D and dB, and that slope tells us which state it is. And we indeed tried that. I'm not showing the data here, but it does follow that trend because it is just like a local measurement of conductivity, and that is sufficient. Yeah. Oh, sorry. Yeah.
I suppose this was dual gauge device.
Yes. Yes.
Fitting factor. That's somehow the top gauge HBM, I suppose, affects your data. You are measuring through the HBM. That's somehow affect the data, or just not affect.
Right. That's a great question. So we did a lot of engineering of the top gate, because top gate, if it's a perfect metal, it screens everything, and microwave cannot go through the top gate at all. Then we cannot get those like scanning measurements done. So what we did was we use a monolayer TMD as a top gate, and we use excitonic resonance to drive it into the insulating regime, such that its mobility is super small. It doesn't screen microwave that much, but it's still having enough carrier density to gate the material to whatever that it needs to go. So then we did comparison between measuring just on the top gate and on the sample. So the top gate is insulating enough that it does not affect too much of this measurement. Okay.
Just one other question. I noticed that in the transport measurements below U equals -1, there's a low resistance region, which you don't see in the MIM data. Can you explain?
Yeah, sorry, just to make sure I understand which, by below -1, you mean -1.2?
-1.2 to -1, yeah, that region.
This region?
Yeah.
Oh, so this is this region?
Well, so you pick up the line at -1.
Yes.
You have that, but then just broad region below that, and the transport data, that's low resistance, whereas in the
Yes.
microwave data, it looks high resistance.
Oh, this is actually low resistance. So we're probing conductivity. So this is high conductivity.
Oh.
And low
Yes,
resistance.
of course.
Yeah. Okay. So then I'll go into the spatial map of the device. So the device looks like that. These are the two electrodes. And then the scan region is like the yellow region. The flake edge, as denoted by this blue dotted line, so that's the horizontal line. There's also an interface region. I won't go into detail about that. So then what you can look at is just like the flake edge here, and see how the signal changes on the flake edge and then inside the flake, which is underneath. So that's kind of the spatial map. Okay, so we first went to the integer quantum anomalous Hall states by just like changing the top gate voltage and the bottom gate voltage, and that follows this green arrow. And by following that, we map out the signal from nu equals to minus 1.3 to minus 0.78. And as you can see, so at nu equals to minus 1.3, or the other extreme, it's pretty homogeneous and conductive everywhere. But in the middle, when it's close to nu equals to minus 1, there's a sharp contrast between the edge, it's over here, which is bright, which means conductive, and the bulk, which is pretty dark, so it means insulating. So that is the signature of the quantum anomalous Hall edge states at nu equals to minus 1. Then we also went to the fractional fillings by changing the parameter in this parameter space following the green arrow that traverses minus 2/3 and minus 3/5. And now if we look at it again, goes through minus 2/3 over here. And once again, from homogeneously bright, it becomes the edge being bright and the sample or the bulk being dark. And similarly, near nu equals to 3/5, it's still this bulk edge contrast. But what this contrast tell us has to be sort of verified by driven this topological phase transition. So here, the advantage of working with material is the displacement field is a nice tuning knob. So if we follow this green arrow, we'll fix the filling at nu equals to minus 2/3, and then just like drive the displacement field from very negative to 0 to very positive. So what we saw there is that from homogeneously being insulating or dark means insulating, and then this is also insulating on the other side. In the middle, this is only in the topological phase where you can see the edge being conductive and the bulk being insulating. So this is confirming that we did see a topological phase transition, and the edge state is not always there. So then we went into a little bit of detail of what this microwave signal is actually telling us. And of course, we don't have a concrete answer to this question yet, so more theoretical insights will be welcomed here. We first tried to fit into the single mode edge picture. Namely, there's just one nu equals to like a 2/3 edge state. And then it doesn't have those like hierarchy states. It doesn't have a reconstruction or anything. Then what this microwave signal carries at the edge would be two parts. One part is the edge magnetoplasma. There have been theories taking care of this, showing that inside this like 0 to 100 gigahertz regime with the parameter that we have, it has many resonances. And the resonance frequencies are different for different edge states. It depends on the charge, and it's proportional to the effective charge squared. That's one part of contribution. And there's also another part of contribution coming from the ohmic loss. So this material is not perfect, and the mobility is also not very high. So there are a huge part of contribution coming from sigma XX residual conductivity. So the ohmic loss part and the edge magnetoplasma part would form the major contribution of the edge signal that we saw. And then we can provide like theoretical predictions of what type of signal magnitude we can see for each of those states. But then we saw deviations from it. We were supposed to see that nu equals minus 3/5 being much larger in amplitude than the nu equals to minus 2/3 than minus 1. It seems like it's not exactly the way that we thought it would be. So then we kind of just like dig into the literature for the fractional quantum Hall edge models. So inside all those like composite edge models, you have like Gervin-McDonald model with one downstream mode and one upstream mode of 1 1/3. And there could be also the kind of the disorder equilibrated, the Kien-Fisher-Polchinski model with a neutral mode and a 2/3 charge mode, or even the more complicated mirror picture. Moti has talked about it earlier today. So as of now, our signal or our data is not enough to conclude like which model is it really pointing into, unless we have a way of measuring this like neutral modes on the site. But indeed, what we found was some similarities with what Kian was saying. This leads to a charge mode. So he meant that this type of equilibration or the interaction between the two edge states lead to a charge mode that propagates with a dispersion with a diffusion constant, namely that now the magnetoplasma propagating at the edge has a different effective velocity. I should say the resonances and everything would be different. So then it is kind of, so what we saw is kind of in agreement with this type of composite edge models. But yeah, as you can see, there are a lot of like mysteries or questions that are still there because our techniques are still kind of limited. And there are different limitations. And one major limitation is in many cases, to identify the physics underneath, we need the conductivity in the microwave regime as not only a function of frequency and a function of spatial coordinate. So it has dispersion in these two subspace in the same time. But because of the impedance matching, because of the technical issues, combining spectroscopy and microscopy have been deemed pretty hard. And this is another theoretical prediction saying that all chiral-Majorana edge modes have distinct features of conductivity in this regime. But once again, it needs you to somehow park a tip at the edge and also measure it as a function of frequency. So that's kind of hard. And then there's another thing that's kind of hard, which is the sensitivity. Comparing to DC transport, you might have really good understanding where the quantitative measurement. Here, we also try to measure or to find those even denominator fractional translating states. In our MIM measurement, when we cool down the sample a little bit more to 500 millikelvin, what we saw was that there were more states from the gene sequence surfacing, and that was kind of expected. For example, the minus 4/7. But then we also saw a small dip at near close to minus 1/2, only at specific spots of the sample. And there's a little bit of a dip on the other hand as well at near close to minus 2/5. So that just drove us to think like whether there are possibilities that we can give our technique more sensitivity such that it can be a better probe of those like fragile or smaller gaps in the materials. So this drove us to do some instrumentation in the past year. And now, instead of having the sample there and then the tip capacitively coupling to the sample, we put the sample on a silicon photonic crystal. So here, this is how the silicon photonic crystal looks like. It has a periodic modulation of the refractive index, and that makes it possible for forbidden transmission in a range of frequency. And then those dots, as you can see here, that's point defects. And those point defects can trap electric field effectively. So that's to say, if you put on a sample somewhere close to the center of this whole thing, then you can have a huge enhancement of field. And that is one way of increasing the sensitivity. So here's what we did. We put on this field layer graphene encapsulated by HBN type of device, not device, just like dry transferred material onto this silicon photonic crystal. the black region here, there's this one hole, and the other side, that's another hole. So that's sample on top. So then now what we measure is the dissipation or the loss caused by the material, and also the frequency shift of this cavity caused by the material. So the dissipation has two parts. One part is just like the internal coupling rate, dependent on the geometry of this cavity. But then also the sample will give rise to another part of it. Similarly, the frequency of this whole thing, so this is very similar to this like superconducting resonator sensor of MATBG, but it's a different type of cavity. So the frequency is proportional to 1 over square root of the effective permittivity and permeability. And the sample, when put onto this photonic crystal, can effectively change the permittivity. So this is how it looks like. So when you have no sample, so this is a black curve, this is the forbidden band region, and then those very sharp resonances are just like by design. And then the red curve or orangish curve, so that's when we put on the sample and measure the transmission between this port and that port. So that's S21. And as you can see, there's a little bit of frequency shift. So these are the zoom-ins at specific frequencies of the resonance. And then there's a shift, and also the peak broadens. And so that's a type of measurement to say that, oh, the sample caused more dissipation. Okay, so this is a measurement that we try to increase the sensitivity of the transmission. But we also wanted to incorporate microscopy into it. So what we did was we put the tip onto a tuning fork, and so this is the tip, and we made it really close to this photonic crystal. In the specific case, we just like didn't etch the holes, but instead this is a waveguide, so it allows a broadband transmission in the millimeter wave region. So, and here we hover the tip on top of the sample, and that's where the microwave or millimeter wave comes in. And then we use one of the ports to collect the millimeter wave coming out. And that's what we get. So it seems like now we can also do scanning measurements at 92 gigahertz. And so this bright region, which means the sample is more conductive, has a good coincidence with the graphene boundaries. Let's just say you can scan those like materials readily here and there, while HBN just doesn't have that response because its conductivity is really small, similar to this background like silicon conductivity. And then in the real channel, because the graphene is a pretty good conductor, it just doesn't show too much of dissipation. So that's as expected. But more than that, because of this photonic cavity design, we can now do frequency sweeps. So there's 92 gigahertz and there's 100 gigahertz. They look kind of similar, but yeah, because there aren't specific modes of graphene inside this regime, but we can now do the whole W band from 75 gigahertz to 115 gigahertz. So that's just like the first step of reading out all those like different modes and fragile states in this frequency regime. And also because we're using like a dielectric type of cavity, so it's finally compatible with magnetic fields, and it can be done at all types of temperatures without needed to be limited to be below TC for this type of sensing. Okay, so that's one type of technical upgrade. There's another type in the field through dispersive readout. So, and the dispersive readout means like measuring a state without exciting or destroying it. So then you have the RF wave coming in, it goes through a resonator, and your detector reads out that resonator. So this is your whole measurement circuit. And what you do, instead of directly putting your sample onto that circuit, you put it close to that circuit. It could be a qubit, it could be a sample, but then the idea is that you don't allow them to, okay. You don't allow them to have, yeah, the slides did not allow me. Okay, so no energy exchange. And when there's no energy exchange, your readout would really not perturb your qubit much. So same for other samples or modes. So in here, but then you still have a coupling constant between these two. And this G is the coupling constant. And this omega R minus omega Q, that's like the frequency detuning or the frequency differences between your qubit resonance and your resonator's resonance. And this chi is what the frequency shift of this resonator rates out to be. So that is to say, instead of directly measuring this thing, you measure something right close to it, and that's a resonator. And because there's no energy exchange in quantum measurements or information, they call it the quantum demolition, a non-demolition type of measurement. And this can be very helpful for measuring many like macroscopic coherent states in condensed matter as well. And here's the other regime. So just now I described this weak coupling regime. And now we also have this strong coupling regime. What if we just don't want that mode to be there anymore? We want to destroy it and couple it and form something else. So then here, the microwave cavity or the resonator can be a hub. And then you can couple to a magnon, couple to a nanomechanical resonator, can couple to a two-dimensional electron gas because it has like edge magnetoplasma modes and other modes. You can couple to transmon qubits and many more. So here in the strong coupling regime, that's to say the Hamiltonian is written as you have this cavity, the all second quantized version, and then you also have all your modes. It could be a magnon mode at omega j and to dag whatever, and then you also have this strong coupling Hamiltonian term. And when re-diagonalizing this Hamiltonian, you will get new modes coming out. It could be a Plareton mode. It could be other type of energy, like chain exchange between all those things. And here the strong coupling criteria is when your coherent energy change is larger than a loss. So that's to say, before it decays, there's already different rounds of coherent energy exchange happening. So that will enable a lot of like new possibilities of interfacing quantum information and quantum materials. Like for example, can we use the magnon in a magnetic material to do the energy storage in a quantum circuit? This type of things. Okay, I'm right on time, great. So here comes the summary. I started with some fundamentals of how to probe microwave and what to probe, essentially the different material responses. And then gave 2 examples on superconductors and fractional quantum Hall states using spectroscopic and microscopic measurements individually. And then introduced some new methods of millimeter wave sensing, dispersive radar, hybridized quantum systems. And here are some open questions. There are more million-dollar questions, but among them, can we directly sense and control those non-abelian quasi-particles with microwave fields? And how far can we push the quantum limited nanoscale microwave imaging? So all that will be on the interface of quantum information and quantum materials, and hopefully can really dig into new physics that was previously not achievable. Okay, with that, I would like to thank, because I presented a lot of data today, my collaborators, mentor, and mentees at Stanford University, University of Washington, NIMS, and UC Berkeley. And I adopted a lot of content from this book, Microwave Engineering, Pulsar. So if you're interested, you can check it out. Thank you.
I guess we have some time for questions.
Yeah, hi. Thanks for the nice talk, and I have 2 questions. So first question is like, when you're like measuring the fraction change with phase in, for example, T2 with MIM, you claim that your observe like some kind of like edge state. Why does the edge state is kind of frozen in a real space? That's my first question. And my second question is like, did you also see any signature or like superconductivity in MOT in MIM?
Thank you for your questions. So first of all, for your first question, why the width of the MIM that we saw is wide? Well, the short answer is the screening is poor. Like if your screening is very good, then you would be able to see an edge on the length scale of a magnetic lens. But in our case, we deliberately designed it to have a crappy top gate because we want microwave to go into it. And we had a sample with not high enough mobility. So that's kind of the status of using twisted sample to see this type of fractional state. The mobility is not comparable with like graphene monolayer or to say gallium arsenide. So then you have a lot of loss in that case. So these two together just made the edge state wide. Yeah, so this is the first question. For the second question, did we see superconductivity? So we didn't see superconductivity. Our current measurement scheme with MIM is not super compatible with measuring superconductivity. So those new schemes can, but the old schemes cannot. The reason is we are only sensitive to a range of conductivity, but then we're not sensitive to inductance that much. So then, because the tip is capacitively coupled to the sample. And that made it hard to tell the difference between a conductor and a superconductor.
So in your MIM measurement, you can actually see the edge state in the sample's edges, right? And I'm wondering what's the resolution of your microscopic scanning, and also can you see like if there's two edges or one edge for the two third states, like in the different models?
Yeah, so that's a good question. So our tip resolution is 15 nanometers or so. So that's also reported in the paper that you can see that we were able to resolve some of the small features on the scale of like 50 or 100 nanometers. So that's how we kind of determined the resolution there. But for whether we can resolve like the bunch of edge states, that's gonna be much harder. So that comes back to the screening question. So we need to somehow screen it very well so that we have sharp edges, we don't have too much broadening. And also we want to avoid being too close to those like magnetoplasmon resonances, because its width of those magnetoplasmons are also kind of determined on the perimeter of the sample and other parameters of it. So if we can achieve these two together, good screening, not too close to those resonances, we might be able to see those different edge states. So because previously MIM was able to resolve the quantum Hall edge states as different stripes. So it might be possible, just technically need some modifications.
I see. So like you said, one difficulty is the quality of your top gate, and because you need to use like the TMD and you stop. Is it possible that you don't use the top gate, but instead you go high enough magnetic field to see the fractional states?
Do you mean in graphene instead, or like gallium arsenide, like in regular quantum, fractional quantum Hall effect? Yes, that's completely possible. Yeah. So we might be on the road. So previously there were some just pure technical reasons that we did not go down to very low temperatures yet. But now that we can go down to dilution fridge temperatures, it becomes much easier to see those fractional states directly.
Thank you.
Thanks, great talk. I want to ask about the imaging of two-third edge states.
Yeah.
So just to make sure, so with this microwave impedance imaging technique, I guess you can only see the charged modes. Is that correct?
Yes.
Also,
basically, do you have any thoughts on how one may image neutral modes or have something direct way to see it? Because you mentioned that
Yes.
maybe some results favor the Kingfisher-Brzezinski prediction. That part I don't fully understand. Like, what part is consistent with
Right.
Kingfisher-Brzezinski, and can you elaborate a little more, please?
Yeah, sure. So I think Moti will talk about it tomorrow, how to image the charge neutral mode by thermal transport. Is that true? Tomorrow. Yeah. Okay. Yeah. So I think that's a better way of doing it, because like microwave only couples, if we are really measuring its reflectance, only coupled to those charge modes. So unfortunately, it's not super direct. But yeah, we can maybe combine different methods to get a better understanding of the edge. So then for your second question of which aspect made us feel like it's KFP or something. So it's like, just in this description, it says that we cannot directly use the regular magnetoplasma calculation to calculate the intensity of that mode. So we previously tried that calculation and we saw our data deviated from it. So we're thinking that it might be that the composite edge models or the edge reconstructions playing a role there. So it's sort of in accordance with the theoretical prediction, but it's not the other way around. It's not we're saying that, yeah, this is KFP.
Are you aware of existing calculations using Kingfisher-Brzezinski starting point to calculate experimental signature of MIM?
Not yet.
Not yet.
Yeah, maybe you can do.
Thanks.
One more question. Thanks, Max. Actually, I have another question regarding the very first one about the width of edge states. So how should I understand the local conductivity from a theoretical point of view? Should I view your images as the distribution of the charge density, or should I view it as distribution of the expectation value of the current density of the given thing?
Yeah. Maybe none of those. So neither of those. So what we're measuring is the impedance. So that's kind of like the definitely true, that because this is how we measure reflectance. Reflectance has to do with the impedance. So then the next question is what the impedance has to do. And usually the impedance has to do with the conductivity. But in the case of a 1D Lottinger liquid, it has a slightly different form. So then, so the Tiger has a theoretical paper on that, showing like how is it directly connected to all the parameters of the Lottinger liquid there. Yeah.
So let's thank the speaker once.